now that we know how to create that, how to put together that compliance matrix, we know that any state of stress we come up with, we can calculate the strain. So as long as we can come up with the stress, we can figure out everything about the deformation and everything for the kinds of materials that we're dealing with. And so now we're in the process of figuring out how to calculate stresses, the state of stress at a point in a material. And the easiest one was uniaxial tension and compression. I want you to think for a second about the stress strain curve or graph. So if you have stress on this axis, say the XX stress, and strain on this axis, the XX strain, draw a quick sketch of what you think this curve would look like. Okay, so that's right. So we are requiring that there's a linear relationship between stress and strain. So that's exactly right. So at least at the start, it's going to go from, so if there's zero stress, there's zero strain. So it's going to start here. It's going to go up like this. Okay.
Then it'll branch off to the top.
Yep. Yeah, so it's going to get to this point, and at this point, so this is the linear elastic range, the linear elastic region. This is where this class applies. Okay. Once it gets to this point, it starts to, and I'm talking about a metal, probably other engineering materials have similar graphs. There are little changes in how steep things are or whatever, but so it'll start to tail off like this. So it'll start to become nonlinear. And then something will happen, and finally it'll reach this point called the yield point. And then finally it'll fracture. All of this, so this linear elastic region, if you remove that stress at that point, remove the loading, anywhere in the linear elastic region, that strain disappears. So it goes right back to its original shape. In this region, you have plastic deformation. That means if you remove the loading, it doesn't return back to its original shape. The way you would produce a graph like this is, a more sophisticated version of that contraption that we set up in class the other day. We could have come up with a stress strain curve for that rubber band if we would have kept adding loads to it and just little by little kept measuring the strain. We would have gotten a curve that looks like this. So there's the stress, there's the strain, and we would have gotten something that right from the start was nonlinear. So this would have been like a rubber band. No linear region. Even though in this range it's still elastic, if we would have removed the loading, it would have returned to its original shape. For materials like this, you can't use the equation that says the Voigt stress, I have it backwards, the Voigt strain is equal to the compliance matrix times the Voigt stress. Okay. Yeah, question?
We apply this linear relationship with only on the linear relationship, the formula.
That's right. Only things that have a linear region like this are what we're dealing with in this class, because that linear relationship between stress and strain is one of those 4 assumptions that we make in this class. Okay. All right. So I have an example problem now that I would like you to work on. So let's say that you have a equilateral triangle that's made up of these 2 bars. Pin joints here and here. Each of these is 1 meter long. And they're 1 meter apart. Let's call this member 1 and this member 2. And let's say there's an external load of 15,000 newtons. The cross-sectional area of member 1 is, well, I guess not the area, the cross-section of member 1 is a square with side lengths of 0.05 meters, and the cross section of member 2 is a square with sides of 0.02 meters. And the questions are, first, what are the stresses in each member? And second, where on each member are these stresses believable? Okay, so in statics, you know, I didn't really like to do problems where we neglected the weights. We're going to neglect the weights here. Why am I, there's a reason why we have to neglect the weights. Why is it? In order for you to do this problem. So think about, think about when we calculated the internal loads of beams where we included the weight. What changed when you went from neglecting the weight to including the weight? Remember, that was one of the problem sets we did.
Was it linear?
What happened was you had when we included the weights, you went from being totally in tension and compression to starting to have shear forces and bending moments. And right now, we can only calculate the stress if the only loads are tension, the only internal loads are tension compression. Okay? So the fact that I made this a simple truss with no weights means that each of these two members is going to be loaded in tension or compression at the two pins. And that means we can use the calculations that we just did. We're going to need new ways to calculate stresses for beams that have other internal loads besides tension and compression. Okay. So this is like